Okay, thank you so much for being here, and thank you, Nicole, for inviting me to present this lecture. I should mention here that the second part of this lecture will be joint work with Schweinberger Batra, who's sitting right there. And so let me start off with a beautiful tree. So this tree represents a bunch of words. For example, war and peace, social media, human brain, artificial intelligence, causal learning, markets, global economy, pandemics, trade, and a bunch of other things. So what do all of these things have in common? So what's a common thread in all of these concepts? Arguably, the common thread here is that all of these things have an underlying network which affects outcomes of interest. And I will explain this in some selected examples, starting with the global economy. So the global economy consists of markets, so financial and non-financial markets, which are basically exchange networks in the sense that people, institutions, companies, governments exchange goods and services. Markets are therefore exchange networks. And these exchange networks affect many outcomes of interest, in particular the economic welfare of billions of people around the world. In fact, if the global economy shut down today, then we would all be in deep trouble. So that is one example where you have an underlying network, and the network, the markets, affect outcomes of interest. A second example is war and peace. So you have many state actors and non-state actors, such as insurgencies and terrorist groups. And relations between these state and non-state actors can affect the welfare of nations, and in particular, war and peace. So again, you have an underlying network of relationships between state and non-state actors. And these relationships have an effect on war and peace, and therefore the welfare of nations. A third example is epidemics and pandemics. So infectious diseases are spread by way of contact. No need to mention any particular one. So again, you have here a network of physical relationships between people. An infectious disease can spread from person to person, and from person to animal, and animal to person by way of contact. And this has a huge effect on the health of individual population members, as well as public health, and possibly also the economy. So again, there's a network which affects many outcomes of great interest. A fourth example is the human brain. So the human brain consists of neurons, and these neurons interact and cooperate in order to achieve complex tasks, such as writing, doing mathematics, inventing things, and so much more. So again, there's a network of interest, and the network of interest has a huge effect on outcomes of interest. In this case, our ability to be human beings. A fifth example is artificial neural networks. So the human brain, which is a neural network, has inspired artificial neural networks, because when people started looking into how to build artificial intelligence, they were wondering, how can we build artificial intelligence? What is the best form of intelligence that we have? And that is the human brain. And so some of these researchers were inspired by the human brain and attempted to build artificial neural networks, which basically process certain inputs and produce certain outputs. For example, it takes an image and it produces similar images. And last but not least, among many other examples, is causal inference in connected populations, where you have networks that capture the cause and effect between treatments and outcomes of interest, as well as spillover in connected populations. And in fact, this is basically the one which I will focus most in the second part of the talk. Okay, so first I will start off with a short discussion of graphs as a useful representation and mathematical abstraction of networks and connected systems. And I will do this by going back to this classic problem by the mathematician Euler in 1736. So Euler basically walked through Königsberg in Prussia, which is modern-day Kaliningrad in Russia. And he was basically wondering, if we start anywhere, for example, let's say we start in this neighborhood, can we cross each of these bridges over this river once and return to the starting point? And that is a classic problem in graph theory, the first problem that was formulated as a graph theoretic problem. And the answer turns out to be no. You cannot start somewhere, cross every bridge once and only once, and return to the starting point. This is a nice problem, not so much because the question is of such great importance, almost 300 years after it was posed, but because it is a great example of how a great mathematical scientist, a great statistical scientist, and a great scientist actually works. And what you can see here is basically an abstraction of the essential features of the problem. So first, by separating the inessential features from the essential features, and then basically using the essential features of the problem to solve to answer the original question of interest. In this case, the specific three-dimensional structure of these neighborhoods is not material. The streets, the houses, the people are not essential for answering the question of interest. All you really need is basically the four neighborhoods: this neighborhood, that one, and that one. So that's four neighborhoods, which we can represent by 4 points or 4 nodes, and the 7 bridges, which we can represent by 7 lines or 7 edges. So these 4 points and 7 lines are all you need to answer the question of interest. And that's what a great mathematician does, extract the essential features of the problem and separate them from the inessential features. So basically, the original problem, which is a 3-dimensional structure, is reduced to this graph where we have 4 points and 7 lines, which helps us to answer the question. And since Euler's work, graphs have turned out to be a very useful mathematical representation of connected systems of all sorts. I mentioned some of these connected systems already, and I will briefly highlight some of them in more detail. So here's markets. So markets are of great importance because the global economy affects the economic welfare of billions of people around the world, and it's powered by people, companies, and governments interacting with each other and exchanging goods and services. So in this simplistic example, you see 3 companies labeled 1, 2, and 3, and you see arrows between them, which represent, for example, which represent certain exchanges. So for example, company 1 might sell certain goods to company number 2, as well as company number 3. And then company 2 manufactures something and sells this to company 3. So that's a simplistic version of the global economy. Of course, the global economy consists of millions of companies worldwide, people, governments, and much more. But you can basically use graphs to represent the global economy or the exchange of goods and services worldwide. Each of these edges can have not only direction, but can also have numbers attached to it. So for example, it might be that company number 1 sells 1 million goods in the amount of 1 million to company number 2, so that then there would be 1 million here, and company number 2 would basically sell goods in the amount of 2 million to company number 3, so there could be a weight of 2 million attached here, and so forth. You can also have multiple edges between them, directed ones, undirected ones, and so much more. So this is a simplistic version, but you can see that that markets and the global economy can be represented by networks or graphs. So here's one of the other examples I mentioned before, the human brain. So the human brain consists of neurons, and here we represent neurons by x1, 2, and 3. So these are 3 neurons in the human brain. In practice, in the real world, the human brain has many more neurons than that, but again, this is a simplistic version. And these neurons interact with each other, which is represented by these lines. So these represent lines or interactions between neurons. And these interactions enable the brain to perform complex tasks such as walking, talking, writing, mathematics, and much more. The human brain, in turn, has inspired artificial neural networks. So the human brain is a neural network, and it has inspired artificial neural networks. This has a long history dating back to the 1940s and 50s. So this is not a particularly new idea, but it's an important idea. And here the nodes represent, for example, input X, output Y, and artificial neurons, H1, 2, 3. So basically, we have some input, which could, for example, be an image. And the image will basically be processed by an artificial brain. The artificial brain consists here of 3 neurons, 3 artificial neurons. And these artificial neurons do something with this input and then produce some output, which could be basically a bunch of similar images, for example. Of course, again, this is a very simplistic representation of the problem, because many of you who have heard of artificial neural networks know that you might not have only one layer of artificial neurons, but you might have many layers, and within each of them, you might have hundreds or thousands of artificial neurons. In total, you might have millions of artificial neurons in this artificial brain, but that's the basic idea. So that's, again, another important problem where you have networks involved. And last but not least, there's many others, but this one will be the last one I mention here. Last but not least, graphs can represent cause and effect. So for example, here the nodes correspond to the treatments X, outcomes Y, and confounders C. And the edges correspond to causal relationships between these treatments, outcomes, and confounders. For example, here's a beautiful case study by Chris Jensen, published in 2022 in the Journal of the American Statistical Association. In this beautiful case study, they basically studied the causal effect of X, which is conflict, that is armed conflict between armed group insurgencies and the government, and Y, which is the forest loss and the rainforest. And the confounder here is C, which is the accessibility or the distance to the nearest road. And here you can see that there's a causal effect from X, which is armed conflict, on Y, which is forest loss. And both of them can be affected by the distance to the road. So for example, the distance to the road can increase the likelihood that there's conflict. At the same time, the distance to the road can also affect the outcome of interest, which is forest loss. Because if you're in a remote region of the rainforest in Colombia, then there could be more armed conflict, but there could also be more forest loss, because there might be criminal gangs which basically cut down wood and sell it for profit. So again, there's a causal effect of X and Y, but there's also an effect of the confounder, which is the distance to the road or the remoteness, which affects both of them. So there's like I said, this was published in the Journal of the American Statistical Association back in 2022. Now, the second part of my talk will be about one case study, which is concerned with something related to the previous example, but a little bit more complicated. And this is what the title of my talk is, Causal Learning in an Interconnected and Interdependent World. So I will use here a toy example involving teenagers who are targeted by advertisements featuring design clothes on social media. So in other words, you have some advertisers who basically advertise certain designer clothes. The advertisers would like the teenagers to buy these designer clothes and therefore target them on social media. So basically, if you're on social media and you're a teenager, you might get to see certain ads. And in this case, the treatment is basically whether or not a teenager is targeted by an advertisement of designer clothes. So basically, whether or not the teenager gets to see an advertisement of designer clothes. The outcome here is could be whether or not the teenager spends money on designer clothes. In particular, for example, teenager A might purchase designer clothes in the amount of YA dollars. So this could be the outcome of interest. And spillover can occur in these situations because teenagers are not independent. They are basically connected by friendships. And so it could be that if you target teenager A, there might be a spillover effect from teenager A on other teenagers B who are friends of teenager A. And this means that other teenagers who have not been targeted, but who are friends of teenager A, might spend YB dollars on designer clothes. I will explain all of these features in more detail in the next couple of slides, but that's the basic setup. So to make things a little bit more specific, I will introduce a simple model, a simple but non-trivial model. And that is basically based on the assumption that the treatment assignments here, that is whether or not a teenager is targeted by advertisements on social media. This treatment assignment is called XA for teenager A, and it is equal to this check mark if teenager A is targeted by advertisements on social media, and otherwise is equal to this red cross if the teenager is not targeted by advertisements on social media. So the outcome is called YA, and we assume here as a simple starting point that the expected potential social outcome YA, which depends on the treatment of teenager A and as well as the treatment of teenager B, can be written in this form. So this is a weighted sum. So we basically assume that the outcome YA of one teenager A basically depends on a constant plus an effect of the treatment XA on the outcome of teenager A. Here, beta is a weight which can either be 0, in which case there's no effect of treatment at all, or it can be negative or positive. The higher beta is, the stronger is the effect of the treatment XA on the outcome YA of the teenager. In addition to this direct effect of treatment, of the treatment of of A on its own outcome, there could also be an effect of the treatment of other teenagers who are friends of A on the outcome of teenager A. And this is called treatment spillover. I have a plot in a slide or two, but we assume here that this is basically a weighted sum of the treatment assignments of other teenagers B who are friends of A. So CAB is basically an indicator of whether or not B is a friend of A, and it will be equal to 1 if B is a friend of A, in which case you have an additional effect of the treatment of XB on the outcome of A. So this is basically spillover in the sense that your treatment can affect my outcome. And this is called treatment spillover. Then there's an additional effect which is called outcome spillover, which is when the outcome of other teenagers B affect your outcome, provided that these other teenagers B are friends of you. Now, this is maybe best seen by using this graphical representation. Again, that's why graphs are useful. We're talking here about causal inference and connected populations. So we can represent the problem by two graphs. The first graph is sometimes called the interference graph. And the interference graph corresponds here to the networks of friendships between the teenagers. So in the simplest case, let's just assume we have two teenagers to keep it very simple. If you have two teenagers, A and B, then the line between A and B indicates that A is a friend of B and vice versa. So this is a friendship network, and it basically enables spillover because if B is a friend of A, then B can affect the outcome of A, and A can affect the outcome of B. So there can be spillover. And therefore, this is called the interference graph. Now, given this interference graph, which is corresponds to the friendship network between the two teenagers, A and B, we have a causal graph which basically represents cause and effect. And in particular, it captures two forms of effects. So here, XA is the treatment of teenager A, and XB is the treatment of teenager B. YA is the outcome of teenager A, and YB is the outcome of teenager B. You see here a bunch of arrows which basically indicate which capture different kinds of effects. So there's a direct effect of the treatment XA on the outcome YA of teenager A. This is indicated by this black arrow pointing from XA to YA. Likewise, there's a direct effect of the treatment XB on the outcome YB, indicated by this black colored arrow. In addition, you see two green colored arrows. So this one is an effect of XA on the outcome YB. So this is basically treatment spillover. So the green arrows indicate treatment spillover in the sense that my treatment XA can affect your outcome YB. Likewise, your outcome, your treatment XB can affect my outcome. So the cross arrows indicate treatment spillover in the sense that my treatment spills over to you and vice versa. In addition, we can also see here this orange line here. So this orange line corresponds to outcome spillover. So this could be because my outcome might actually affect your outcome. So there could be many reasons for this, but a simple explanation is this. So for example, if if I'm not targeted by, so if XA, if I'm not targeted by advertisements, but you are targeted by advertisements, then I might, then you might start purchasing many designer clothes. So you spend a lot of money on designer clothes. So you have a high value of YB. And I basically see that you are wearing these designer clothes and they look very nice on you. So I decide, I also want to purchase them myself because they look really good. So I've not been treated, but I might basically decide that, well, these designer clothes look really nice. So I start buying them myself. In this case, your treatment would basically affect my outcome or would increase my value of YA. So I might start purchasing many designer clothes myself. So this could be one possible effect. So basically observe that you purchase design clothes and that they look nice and I like them and I start buying them myself. Another one could be peer pressure. So if you start basically upping in the game and purchasing a lot of design clothes and you dress really well, then basically there might be peer pressure on me to do the same thing and basically also dress up. Because if you dress up and I don't, then I might look really crappy and you might basically start deciding that I'm not a good friend of you. So due to peer pressure, you could, I might also start purchasing more design clothes. Right? So this is among teenagers, of course, not grown adults like you. Okay, so basically there's multiple explanations of why this could happen. But one thing I briefly want to emphasize here is that there's basically multiple effects. So the direct treatment effect of XA on YA and XB on YB, the treatment spillover, as well as the outcome spillover, which could be due to peer pressure or other mechanisms. So the directed arrows indicate causal effects, and the undirected line indicates correlation, not causation. So the undirected, so basically outcomes spillover gives rise to correlation, not to causation. If you want to basically identify causal effects of YA on YB, we would have to have repeated observations, for example, temporal observations over time. If we don't have them, we can't identify them. So this undirected line indicates correlation, but not causation. So basically, there's a bunch of effects in here, and you have to carefully distinguish these different forms of effects. Okay, so in causal inference, there's basically many causal effects that people are interested in. You can distinguish at least two versions, which are called direct causal effect of treatment on outcomes, and the indirect causal effect due to spillover in connected populations. So I will briefly introduce both of them in a mathematical form, and then I will basically show you how we can characterize these direct and indirect causal effects as an explicit mathematical function of the effects of treatment spillover, and outcome spillover, and we will be able to disentangle them and in so doing provide insight. So let me first introduce the notion of a direct causal effect. So there's many causal effects, but here's a simple and natural version of a causal effect, direct causal effect. So it starts with the notion of potential outcomes. So again, pick teenager A, and suppose that teenager A was targeted with advertisements on social media. Then we might wonder, what would A's potential outcome, YA, be if A was targeted by advertisements on social media, and XB is the treatment assignment of teenager B, which could be either targeted or not targeted. So this is one potential outcome. There's another potential outcome because if we do not target teenager A on social media with advertisements, then this would be a potential outcome. So basically, this would be the potential outcome of A, given that A was not targeted and B receives treatment XB. So in practice, we can only observe one of these two potential outcomes, which is the basic problem of causal inference, because either we target teenager A, in which case we observe this potential outcome, or we do not target teenager A, in which case we observe the second potential outcome. So we observe one of them, but not both, which is the fundamental problem of causal inference. And in practice, we might wonder what would be the difference between these two potential outcomes. That is the potential outcome if we assigned A to the treatment group and targeted A with advertisements on social media, versus the potential outcome if we did not assign teenager A to, if we did not target teenager A on social media with advertisements. So again, we cannot observe both of these potential outcomes. And as a result, we will basically average over the treatments, in particular the treatments of other teenagers, B. So this is an indirect cause effect, or the sum of these things will be the indirect cause effect, will be the direct cause effect. And the indirect cause effect will be defined in a similar fashion. But this time, we will basically look at the effect of the treatment of A on the outcomes of other teenagers. Basically, that captures the spillover effects. So suppose that teenager A was targeted with advertisements. Then we basically ask the question, what would the effect of A's treatment on B's potential outcome be? That is YB, which is the potential outcome of teenager B, given that A was targeted with advertisements on social media and B had been assigned treatment XB. And we will compare this to the second potential outcome, which would result if A was not targeted with advertisements and social media. And basically, we will compare the two by taking the difference and averaging over the possible treatment assignments of teenager B. Again, the fundamental problem of causal inference is that we can only observe one of these potential outcomes because either we assign A to treatment or we do not. So we observe one of them, but not both of them. Okay, so the direct and indirect cause effects can then be defined basically as follows. D is the direct cause effect, which is a weighted sum of these expected differences in the potential outcomes. So it's a weighted sum because in practice we might not have, we do not only have two teenagers A and B, but basically millions of teenagers. Okay, so that's why we sum over basically all of these pairs of all of the other teenagers B. The indirect cause effect, on the other hand, which arises from spillover, is called I, and it's the weighted sum of the expected differences in the potential outcomes for other teenagers B when we assign A to the treatment group or do not assign A to the treatment group. And again, this is basically summed over all teenagers A and B if we have more than two teenagers A and B. Now, we will basically ask a couple of questions here, which are of great interest. So first of all, these are basically the direct and indirect causal effects. And we have seen that we have basically multiple effects in the model. We have the direct effect of treatment. We have the treatment spillover effect, and we have the outcome spillover effect. And they're complicated. And we basically, so one important question is, how do these direct and indirect causal effects depend on the effects of treatment spillover, and outcome spillover? That is the beta, gamma, and delta, the weights of these three different effects. And second, how can we disentangle these three different effects, or the contributions of these three different effects to the direct and indirect causal effect? All right, so so this might look a bit simple, but this weighted combination of the direct effect of treatment spillover, and outcome spillover looks simple, but it's actually not simple, because in our model we have a complicated situation where we have spillover on the one hand, but we also have outcome spillover, and the outcome spillover basically means that these outcomes are all interdependent. So basically, in contrast to most of machine learning and statistics, there's no independent replications from the same source. We have dependent outcomes, and therefore things are not far from trivial. And in particular, the treatment and outcome spillover are intertwined. You can see this because the green arrows affect the outcomes, but so does outcome spillover, indicated by the orange line. So basically, both treatment spillover and outcome spillover affect the outcomes, as well as the direct cause effect of XA and YA and XB and YB. And therefore, these two effects are interdependent. And also, the outcomes are interdependent because of the outcome spillover effect. So for all of these reasons, this is not a very simple problem. We will basically make two contributions. First of all, we will provide insight into how the direct and indirect causal effect depend on these different effects of treatment spillover, and outcome spillover. And second, we will also provide comfort that you can still learn from data what these effects are, despite the fact that we have no independent replications in the classical sense of the word, if time permits. I will at least talk about the first question, may or may not have time for the second question. Okay, so long story short, to answer the first question, we we have derived some mathematical results, in particular Schweinberger has derived some mathematical results, which basically characterize the direct indirect causal effects as explicit mathematical functions of the effects of treatment spillover, and outcome spillover. So keep in mind that we've assumed that the expected potential outcome of teenager A can be written as this weighted sum, where alpha is a constant. Beta times XA is the effect of direct effect of treatment. This is the effect of treatment spillover with a weight of gamma. And this is the effect of outcome spillover with a weight of delta. So, and it turns out that the direct cause effect is simply equal to beta, the weight of the effect of A's treatment on its own outcome. So this is expected and unsurprising. The more important point is that the indirect cause effect, which is the hard part, can be characterized as a sum of gamma plus beta plus gamma times some function A, which depends on the network, as well as the effect of treatment spillover. So we can also characterize this function A of delta, but I will not do this here because it depends on further characteristics of the network, which is somewhat complicated. In addition to the indirect cause effect, which I will interpret in a little bit more detail in the next couple of slides, there's also a total cause effect, which is simply the sum of the direct and indirect cause effect, and is therefore equal to this beta plus gamma plus beta plus gamma times A of delta. I should also mention here that there's some conditions attached to this, so there's no such thing as a free lunch. One of them is that this network of friendships among the teenagers cannot be too sparse, so there must be some friendships there, because otherwise there's no spillover. And if there's no spillover, then we can't identify anything. So it cannot be too sparse, but it can be pretty dense if necessary. Now, in the following slides, I will briefly interpret these results and provide some insight into treatment and outcome spillover and how they affect these direct and indirect cause effects, in particular the direct and total cause effects. So first off, let's start with something simple. So it could be that the direct cause effect D is equal to 0, which happens if the weight beta in this linear equation is 0. So in this case, D is 0, so there's no direct cause effect. But it could still be that there's a total cause effect because we still have treatment spillover and outcome spillover. And in particular, if gamma and this A delta function are non-zero, then we can still have a total cause effect, despite the fact that the direct cause effect is 0. So no direct cause effect, but there can still be a total cause effect, because the total cause effect consists of both direct and indirect cause effect. And even if there's no direct cause effect, we can still have an indirect cause effect. So in other words, if we go back to this picture, so even if there's no error from XA to YA and from XB to YB, there still can be an effect because treatment spillover basically can affect the other person's outcomes, and there can also be outcome spillover. So the second example is when there is a direct cause effect. So there's a black arrow from XA to YB and from XB to YB, but the total cause effect is equal to 0. So this can happen when the beta is non-zero, so there's a direct cause effect. But the total cause effect can be 0 because the other terms can actually cancel out the direct cause effect beta. In particular, you see that we have here the sum of beta plus gamma, and this could still be 0 if gamma is equal to the negative of beta. So basically, the effect of treatment spillover can cancel out the direct causal effect of beta. So there can be a direct cause effect, but 0 total cause effect, because they can cancel each other out. Another example is when it's possible that we have an indirect cause effect. So the indirect cause effect is non-zero, despite the fact that there's no outcome spillover. So the green arrows are gone. So this can happen because we might still have a direct cause effect, and we still might have outcome spillover, in which case the A delta function is non-zero. So in other words, even if there's no treatment spillover, there can still be outcome spillover, provided that we have a direct cause effect as well as outcome spillover. Now, it's also possible that the indirect cause effect is non-zero, despite the fact that we have outcome spillover. So even though we have this orange line in the plot, basically the outcomes affect each other due to outcome spillover. For example, peer pressure in friendship networks of teenagers. it can still be that the indirect cause effect is 0. And this is because basically these effects can cancel each other out, in which case the indirect cause effect will be 0. So for example, one special case would be when the direct causal effect beta is 0, and likewise the treatment spillover is 0. So in this case, basically there's no effect of treatment on outcomes at all. So basically both the black and the green arrows would be gone, in which case there's no effect on of the treatments on the outcomes at all. But it can also be when there is in effect a non-zero effect of beta as well as gamma. So basically there's both a direct cause effect and there's a treatment spillover effect. In that case, it could still be that the indirect cause effect is 0, because for certain combinations of betas and gammas, basically the indirect cause effect still becomes 0. So this is a non-trivial insight. And an additional thing that you might ask is, what is the additional, what is the added value of outcome spillover compared with treatment spillover? And you can likewise answer this question very easily by inspecting these equations. So the indirect cause effect is basically gamma, the effect of treatment spillover, plus the beta plus gamma times the function a of delta, whereas the total cause effect is beta plus gamma plus the same quantity. So if there's no outcome spillover, then basically you can show that this a delta function is equal to 0, in which case the entire red colored term is 0, both in the indirect and total cause effect. On the other hand, if delta is non-zero, then you can show that the a delta function is non-zero, and in this case you will have basically this additional term both for the indirect and total cause effect. So you can interpret this red color term as the added value of outcome spillover compared to treatment spillover. And last but not least, you can see also when you look at these indirect and total cause effects, you can see that basically everything is intermingled here, in the sense that this a delta function, which depends on the outcome spillover as well as the network, this basically is amplified by the sum of beta plus gamma. So the larger beta plus gamma are, the stronger is the effect of outcome spillover on the indirect cause effect as well as the total cause effect. And this basically shows that all of them are intermingled, which makes sense because we've seen the plot. And therefore, but that also underscores why it's important to provide mathematical insight into how these how we can disentangle these effects and what the contributions of relative contributions of these effects are to the direct, indirect, and total cause effect. Okay, so am I still doing well in terms of time? Okay, so I still have time to answer the second question. So the first question was basically, can we provide insight into how these can we provide insight into these causal effects and disentangle these different contributions of the direct effect of treatment spillover, and outcome spillover? And the second one was, can we learn from observations what these direct causal effects are? And so both these betas, gammas, and deltas, as well as the direct and indirect causal effects, D and I. And long story short, under some technical conditions, you can show that we can actually learn them by using some convenient estimators. I will not go into details here, but the true direct and indirect causal effects can be estimated by some estimators delta hat and I hat, which are computed based on data. And you can show that the error in the direct causal effect is bounded above by some constant multiplied by the root of the log number of teenagers divided by the total number of teenagers. And the indirect causal effect has an error which is bounded above by a constant times the log number of teenagers, the root of the log number of teenagers divided by the total number of teenagers multiplied by some quantity which basically quantifies how dense the network is. So the denser the network is, in the sense that the more friendships there are among the teenagers, the higher this number rho will be, which will basically be a good thing and bring down the error. All of this holds when the number of teenagers n is large enough. And this is despite the fact that we have here no independent replications in the traditional sense of the word. So in particular, we're not tossing here coins independently. Very much the opposite. We have here interdependent outcomes. And we have no replications in the classical sense of the word. So despite that, we get we give some comfort that you can basically learn all of these effects from data, in particular the direct and indirect causal effect. And here's a plot which basically demonstrates how fast this error decreases. Or I should have mentioned. So this root log n divided by n approaches 0 as the number of teenagers n increases. So in large populations, this will be close to 0, multiplied by some constant. And here's the plot which demonstrates how fast this approaches 0. So here you see this root log n over n term. And here you see the total number of teenagers. And you can see basically that this error rate basically goes down like this. So if you have thousands of teenagers, the error is relatively small. Now, as I mentioned, we basically have dependent observations because of outcome spillover. So we have no independent replications. So how can we learn these effects from data, despite the fact that we have no replications? So basically, the idea is that even though we have no replications, we have a certain budget for influence. And there's basically two different types of conditions in which we can learn this causal effects from data, despite the fact that we have no replications. And this is also true for many other areas where you have dependent observations. For example, when you have spatial observations or temporal observations, you have some budget. And here we have a budget for influence. And in two situations, we can still estimate these effects quite well, despite the fact that we have no replications. The first one is when we have additional structure, for example, overlapping social circles. So that, for example, that could mean that each teenager has basically friendship groups. You can interpret these groups as overlapping social circles because they are social circles and they might overlap. And each teenager A could basically strongly influence a small number of good friends who move in the same social circles. So in this case, we have no replications, but we basically we control the amount of dependence. So every teenager only affects a small number of other teenagers. The second is mean field conditions, which basically imply that each teenager A can affect a large number of teenagers, but only very, very weakly. Okay, so in both of these cases, we basically have a budget for influence. As long as we stick to this budget for influence, we can still obtain, we can still estimate all of these causal effects, despite the fact that we have no independent replications from the same source. Here's a short simulation study where we compare ourselves to a competing paper by Lee and Vega, published in 2022. So they have also come up with some causal effects, but they're estimating the same causal effects, but they do not consider outcome spillover. And in this simulation study, we have both treatment spillover and outcome spillover, which means that this competing paper is basically based on a misspecified model. Here, the blue line basically indicates the true indirect causal effect, the I that I've shown you, which captures basically the effects of spillover. And you can see that this estimator by these competitors is not well behaved. There's a lot of uncertainty, and also it's centered in the wrong place. And this is our approach. And you can see that the estimates cluster around the truth, and the spread is much lower than the spread of this competing estimator. Okay, so that's basically pretty much all. So main conclusion of my talk is basically networks are pretty much everywhere. They affect the health and welfare of billions of people around the world, and also power science and technology. However, the fact that things are interconnected and maybe interdependent also makes things complicated. But that's why it's all the more important that we basically provide mathematical insight into how things work and why they work. And we have attempted to do this and also attempted to demonstrate that you can still learn these causal effects in these complicated situations when things are interconnected as well as interdependent. So thank you all. And here's my collaborator, Schweinberger, sitting over there. And here's a couple of preprints in case you're interested. A little bit more on the technical end, but they basically to present some more details on some of these ideas. Thank you, Michael, for the insightful presentation. So we now open for the floor for
questions from the audience. As a reminder, if you'd like to submit a question, the link to do so is over there. We'll just read that. So one of the questions we have is, so in practice, how do we estimate the friendships between two teenagers? Do we need to estimate them for each pair of teenagers, or how's that done?
Okay, that's a good question. So we do not assume that we estimate the friendships between teenagers. We assume that we observe them. So for example, we collect data on social media, such as Facebook, and determine whether or not people are friends of each other. So we observe them. We do not estimate friendships between people. One could estimate them based on data, but typically they are observed rather than estimated.
Thank you for your response. So let's move on to the next question. So there is one audience asked that, like, can the definition of causal effect be extended if the treatment is continuous? So let's say the treatment became the amount of effectiveness.
Oh, okay, that's a good question. Yes, so good question. We have not looked into continuous treatments. So I guess it can be done, but you would need a different framework. And there's also other causal frameworks, such as approach based on directed graphical models, which I briefly mentioned at the beginning. But this work is based on either treatment or non-treatment, binary treatment assignments.
Thank you for that response. Another question we have from the audience is, what if we only have partial information about our connections? We only know, like, if some teenagers are connected, but maybe not others. Can we still estimate, like, spillover and direct causal effects in that setting? Okay,
so we have only partial information about the connections. That's a good question. You could, but it would come at a price. And this work basically assumes that we observe the friendships completely, so basically all of the friendships in the population. If you have only a sample of friendships, one could still estimate them, but this would be future work.
Thank you for the response. So there is our audience wondering, is it possible to have no treatment spill over, but significant outcome spill over?
Sorry, can you repeat this?
So is it possible to have no treatment spill over, but have a significant outcome spill over? So
you mean so no treatment spillover would mean that there's none of these directed edges from the axis to the y's, but there's still this orange line. Yes, so this is a special case of the framework we consider, in which case where's it? So in which case basically the gamma would be 0, but the delta would be non-zero. That's a special case of the framework.
Thank you. And another question, for the A delta term, could you talk a little bit about what graph features go into determining that?
Yeah, that's a good question. So the A delta function depends primarily on the heterogeneity of the friendship network in the population. That is the degrees or the numbers of connections of the teenagers in the population. The last point, what goes into the A delta function?
Yeah.
Well, okay, so we're basically assuming here that a certain model for generating this this population network. So we basically assume that there's some kind of probability law which produces these population networks. And depending on the assumptions about this probability law, you get different A delta functions. So it basically depends on what assumptions you're making about the probability law that produces these population networks. And in simple cases, this A delta function is basically a function of the degrees. If you assume certain simple probability laws for the population network. But yeah, this basically depends very much on what assumptions you're making about what is the law that governs these friendship networks among the teenagers in the population. But in many simple cases, basically it depends in particular on how much heterogeneity there is among the friendships in the population, or the numbers of connections of people in the population, basically.
I'm breaking the rules and answering or asking a question here. So, so I have a very high level question. So, do you think that this can sort of can be used to help with potentially designing certain experiments? Because I can imagine, say, in your social situation with the teenagers, suppose you wanted to test something in different schools, and you were trying to decide, okay, should I do entire treatment at an entire school, or should I start doing like groups of teenagers within, but do all schools or something like this? Do you think this can sort of be help to answer this question? I have a very personal reason for other applications, but I was just curious.
Yes, I do think so. We have not done it. There's one work which basically does something similar in a simpler mathematical framework for maximizing social welfare. So you basically assign treatments in such a way that you maximize economic welfare. So there's basically an economics paper which does this, which seems to be going to the direction that you're heading. You could also use this mathematical framework to do this, and this would be very interesting to do, but we have not done it.
And did they talk about the benefits of, so that is to say, you just live with the spillover that happens when you apply to the entire school, like the benefits of that versus having this very pure assignments to entire groups, like were they able to kind of weigh the benefits and of either approach, I guess?
Good question. I don't remember exactly, but these are certainly great questions to ask. And yeah, you can use this framework for asking these questions and basically seeing what kind of treatment assignment mechanism is best for maximizing the the total cost effect, for example.
There is an audience interested in like what is the big questions in this research area, and like maybe ones that is the most exciting to you.
That is a great question to ask. I'm not sure I have an answer. So Schweinberger and I am also writing a survey paper at the moment. So we're asking ourselves the exact same question. What are the exciting things to do in this framework? I think one of the things that is interesting is, well, first of all, what Matthew said, that you basically can design experiments in such a way to, for example, maximize the total costly effect in the population. So that's an interesting question to investigate. Another one is that you might only have a sample, for example, a pilot study, and you basically want to learn from the sample about the entire population, or what the total causal effect would be in the entire population, but only conduct an experiment in a subpopulation. So this is related to the problem of external validity, in the sense that the question is whether you can, so your experiment may be internally valid, but you basically want to know whether it's also externally valid, in the sense that you can generalize conclusions from a sample to the entire population of interest. So this external validity problem is also an interesting direction of future research, which we also started addressing more recently. But yeah, I guess there might be many other ones, but we have, like I said, Schweinberger and I have also been asking ourselves the exact same question. So if you've good, interesting answers, we are happy to hear.
Another audience question. So in general, if you just have multivariate regression and don't necessarily know a graph, does this framework helpful for that sort of scenario or for performance?
Yeah, I'm not sure I follow. I understand the question.
General multivariate regression, and then somebody gave you a graph. Can you use your signal method to, interspill over and get all of these to make it perform better?
Would you repeat the question before you answer it? Or your interpretation of the question?
Yeah, so you're basically interested in multivariate regression, and you basically wonder whether this framework could be useful for improving it.
So,
Um,
I give you general graph, not just a line. I give you graph structure. I give you multivariate regression. Well, there is a lot of spillover between different variables, right? So
Between different variables.
consumer.
But the graph is for the variable spin
Yeah.
or for the unit, for the
Yeah.
variable,
Yeah, for the variables.
okay.
Like there are A, B, C, D, E.
Mm.
Then you have a graph, say this,
Okay.
and then you have one variable fraction. Then you want to put them together in a similar fashion.
To account for the interdependencies of
Yeah,
the.
spill over, exactly.
That sounds like an interesting thing to do. I've not thought about it, but this is definitely a direction of future research.
So suppose your XA and XB are themselves stochastically dependent.
Correct. Yes.
So how do you separate the fact there is an edge in their friends? In the fact, maybe they're stochastic, they have a correlation.
So in this situation, we basically assume that treatments are assigned independently of each other. So your treatment will be independent of my treatment, or your treatment is not affected by my treatment, and likewise for all of the other people in the population. So there's no correlation between the treatment assignments. They're all assumed to be independent.
We have time for one more question. So maybe what is the key takeaway you will give the audience after this talk?
The key takeaway, wow, that's a good one. So I think that the key takeaway is that we are living in a connected world, and because we're living in a connected world, things are often interdependent, and many of the recent global crises are basically examples of this, whether pandemics or war and peace and economics and so forth. So basically, because of this interconnected world, it's important to basically gain insight and learn from data in a situation where you have connections, but also where the outcomes of interest are interdependent. And therefore, it's important to basically provide insight, but also to be able to learn from observations, despite the fact that we have no replications. This is not the only area. There's also other things like climate research where we cannot replicate planet Earth. So there's one observation of planet Earth and nothing else. So this is not the only example, but it's basically one of the examples where we need to learn from dependent observations and also obtain insight into how the world works.